Vsepr, shapes of molecules. Vsepr standing for valence shell electron pair repulsion, and it's a theory. We're looking at the shapes and electron domains with up to 4 charge centers. That's the focus. Shapes of species are determined by the repulsion of electron pairs according to Vsepr theory. Lewis structures of molecules and ions can be drawn, but must show all valence electrons for up to 4 electron pairs on each atom. And bond angles can be predicted from molecular geometry and non-bonding pairs of electrons. Those 3 statements I've taken from the IB syllabus and kind of made them student friendly. Now, it begins by saying shapes of species, that word. And then we're going on in the second statement to look at the structures of molecules and ions. That's the meaning of species. It might not be a neutral molecule under consideration. Again, Vsepr stands for valence shell electron pair repulsion. And the theory states 3 things. Electrons around an atom will repel each other and will become as far apart as possible. Makes sense. Electrons are negative. Like charges repel. In a molecule, the bonds around a central atom will repel each other. It is this that dictates the shape of the molecule. Non-bonded pairs on the central atom have a bigger repulsion than shared pairs as they are closer to the central atom. It's repulsion around a central atom that we're considering. Non-bonded pairs of electrons on that central atom are closer to it and so repel bonded pairs more than bonded pairs repel each other. And double and triple bonds have the same repulsion as single bonds. 2 sets of electrons around the central atom. I'm looking at carbon dioxide, my first example. The molecule is linear and the bond angle is 180 degrees. I'm going to highlight linear. It's too easy to forget, but all in one straight line. My sets of electrons in CO2, the electrons in the 2 double bonds get as far away as they can. That means 180 degrees. That means it's a linear molecule. Same in the molecule ethyne. I don't care, there's a triple bond there. Still around the carbon atom on the left. 2 sets of electrons repelling. Going to be linear. But it's exactly the same for the carbon atom on the right. Linear again. Beryllium chloride, beryllium group 2, only 2 electrons, 2 bonds are made, that's it, linear. 3 pairs of electrons around the central atom. Well, my bonding is now planar triangle. Everything is in the same plane. Bond angle 120 degrees. 360 degrees in a circle. I've got 3 bond angles. Each one will be 120. Whether I've got a double bond, as in ethene, whether I've got 3 single bonds, as in boron trichloride. Boron, group 13, 3 valence electrons. It's using them in making the 3 covalent bonds to chlorine, nothing left over. SO2 also has 3 sets of electrons around the central atom, but one of these is a non-bonded pair of electrons. Let me go down to the first little diagram in red. There's SO2. Oxygen always makes two bonds, group 16. Both oxygen atoms are making a double bond to the sulfur. Sulfur also is in group 16. It's used 4 electrons in making the two double bonds, 2 left over as a non-bonded pair. And that non-bonded pair has greater repulsion than the bonded electrons, and so this changes the bond angle. Now it's going to push the two bonds closer together. The angle between bonds decreases to 117.5 degrees. Oh, horrible number, but generally speaking, we reduce the bond angle by 2.5 degrees for every non-bonded pair of electrons around the central atom. And that shape is now described as V-shaped. It's an upside down V the way I've drawn it, or bent. And that's it for 2 or 3 sets of electrons. With 4 pairs of electrons, the bonding is tetrahedral. Tetra meaning 4. Bond angle, I'm sorry, is 109.5 degrees. But that number we'll encounter a number of times, and you'll become very familiar with it. As the molecule is three-dimensional, we must draw three-dimensionally. The hydrogen at the bottom of the slide is coming out towards us. Hydrogen drawn with a bond indicated by a dotted line is going into the plane of the paper. But my shape, tetrahedral, all of the bond angles 109.5 degrees. NH4+, very similar, same shape. It also has 4 pairs of electrons around, in this case, the nitrogen atom. Bond angle is 109.5 degrees. In the case of NH3, there are still 4 electron pairs around the nitrogen atom, but one of them is a non-bonded electron pair. We have a dative bond formed in the structure above. For NH3, the structure is based on the tetrahedral arrangement, 4 sets of electrons. However, the non-bonded electron pair is still on the nitrogen atom. That makes the bonding triangular pyramidal. I don't have a bond above, I've just got 3 bonds below the nitrogen. 1 in the plane of the paper, 1 coming out towards me, 1 going away from me, giving me a triangular-based pyramid. The non-bonded electron pair has reduced the bond angle to 107 degrees. Now, top of the page, NH4+, bond angle 109.5. Here, 1 bond is replaced with a non-bonded pair. Bond angle is down to 107 degrees. Bond angles are reduced by 2.5 degrees for every non-bonded pair of electrons. Moving on. H2O. 2 bonded pairs of electrons and 2 non-bonded pairs. So the shape is again based on a tetrahedron. Bond angle is reduced to 104.5 degrees because the second non-bonded electron pair, the shape is referred to as V-shaped or bent. Bond angle reduced to 104.5 degrees because of the second non-bonded electron pairs. 104.5. If I go back, 4 bonds, 109.5. Replace 1 bond with a non-bonded pair, bond angle down by 2.5 degrees to 107. Carry on. Replace another bond with a second non-bonded pair of electrons, bond angle down 2.5 again to 104.5 degrees. And those are my shapes. Electron domains are regions around a central atom where electrons are found. In terms of two electron domains, I've got BCl2 below. But the big thing with electron domains, in terms of electron domains, it doesn't matter if the electrons are bonded or non-bonded. Two domains are repelled as far apart as possible while remaining fixed to the nucleus, meaning the bonds are still fixed to the nucleus of the central atom, Be in this case. They adopt an arrangement in which they are at 180 degrees to another, linear 180. Three electron domains. Three electron domains, remembering with electron domains, it doesn't matter if the electrons are in a bond or a bonding system, or if they are a non-bonded pair. Three electron domains means adopting a triangular planar arrangement. You could say trigonal planar arrangement. I see that with BCl3. Three sets of electrons, three electron domains. I also see it with SO2. You might remember we described the shape of SO2 as V-shaped or bent. In terms of electron domains, we don't care that there's a non-bonded pair of electrons there. We'll still regard it as triangular planar, trigonal planar. Sulfur dioxide is bent in terms of its molecular shape, but it's still triangular planar in terms of its electron domain geometry. Electron domains, doesn't matter if the electrons are bonded or if they're a non-bonded pair. And now, 4 electron domains. 4 electron domains adopt a tetrahedral arrangement. Molecule methane has 4 electron domains around the central atom. We have it here. So, 3 diagrams. In the first, methane molecule is tetrahedral in shape. It's also tetrahedral in terms of electron domains, since there are 4 pairs of electrons around the carbon atom. Ammonia in the middle, NH3. Triangular pyramidal in terms of the shape of the molecule, but still tetrahedral in terms of electron domains. There are 4 electron pairs. Water is bent, and its molecular shape and tetrahedral in terms of electron domains. So, bent in terms of molecular shape, tetrahedral in terms of electron domains, because there are still 4 pairs of electrons around the central oxygen atom. 2 pairs are non-bonded pairs. So non-bonded pairs, looking at the 3, affect the shape of the molecule. Doesn't matter whether the electrons are bonded or non-bonded. Electron domains, regions where we find the electrons. All 3 of these are tetrahedral in terms of electron domain geometry. A little bit more. Trigonal, bipyramidal, octahedral. Now, we only need to know the basic shapes when there are 5 or 6 electron pairs around the central atom. If I get 5 charge centers, meaning 5 sets of electrons, trigonal pyramidal. Central atom is X. I've got something above and something below, marked as 1 and 5. And I've got 3 items bonded to X, labeled with 3, 2, and 4. 3, 2, and 4 all in the same plane. 1 and 5 above and below that plane. So my bond angles, 90 degrees between 1 or 5 and any of those 3 in the plane. 120 between any 2 bonds in the plane of the molecule. And between 1 and 5, because 1's above and 1's below, 180 degrees between those 2. My example, PCl5. Again, 3 Cl atoms in the same plane at 120 degrees to each other. 1 Cl in the plane of the paper it's written on, 1 Cl coming out towards us, 1 Cl going into the plane of the paper. My other 2 Cls, 1's above and 1's below. Last, 6 charge centers, octahedral. Octa normally means 8. Here we're looking at 6 charge centers and we're calling it octahedral. Reason: if I can imagine that as a 3-dimensional structure, I've got 4 faces in the shape above X and also 4 faces in the shape below X. 8 faces, octahedral. Here I've marked all bond angles as 120. Let me correct that. All bond angles are 90 degrees. I can see it between whatever is in position 1 and any in position 2, 3, 4, and 5. 90 degrees. 2, 3, 5, 4, they're all in the same plane. 360 degrees to go all the way around. There must be 90 degrees between any of those. 5 and 6, 90 degrees again. You could say 180 between 1 and 6, but we tend to say that all bond angles are 90. Example, SCl6. 2 chlorines, 1 above and below. 2 chlorine atoms coming out towards me. 2 going into the plane of the paper. Finally, 2 quick questions, or 1 quick question with 2 parts. Draw the Lewis structure, 1 thing. Name the shape, 2nd thing. And give bond angles, 3rd thing. In 2 species, 6 points altogether. A lot of points. First one, PCl3. I can see that P is the central atom. It's the first in the formula. Look for it if you need to. Periodic table. Group 15. 5 electrons in the outside shell. 3 of those electrons involved in making single bonds to the 3 chlorine atoms. 2 left over. I've got a non-bonded pair. There's my Lewis structure. It doesn't matter that I've drawn 2 electrons above the phosphorus as dots, and my other electrons either as being in a bond or with lines to represent pairs of electrons. Doesn't matter. Every electron pair is represented. It's a Lewis structure. Name the shape. Well, it's based on a tetrahedron. I have 1 non-bonded pair replacing a bonded pair, trigonal, pyramidal. Be okay if you said triangular pyramidal. Now, basing this on a past paper question, looking at the mark scheme, they would give you anything for the bond angle, anything between 100 and 108 degrees. The 2.5 rule would take you from 109.5 for tetrahedral, subtract 2.5, you're at 107. Well within the range. That always happens. My second example, NH2. N is my central atom. N group 15, 5 electrons. in the outside shell. 1 has been gained to give 6. 2 covalent bonds to hydrogen atoms as drawn in the diagram. Alright, so if nitrogen normally has 5 valence electrons, but the negative charge means there were 6 electrons available, 2 have been used, 4 are left over as 2 non-bonded pairs. I've drawn my Lewis structure. I see my shape, again, based on tetrahedral, but my 2 lone pairs repel more. I'm V-shaped. You could say V-shaped, you could say bent. Bond angle, I'm going from 109.5 down by 2.5 degrees twice, 104.5. It's between the 100 to 106 degrees. That's it for Vsepr. If you got anything out of that, and I hope you did, please hit like and subscribe for more content.